Hello, everyone. So this session will be divided into multiple, I would say, videos because it's a long one, and that way it will be probably easier to go through each one of them separately, understand it, and then jump to the other one. So I will divide them into maybe two or three, depending on how much time it will take me to finish each section of this session. And again, it's going to be easier for you that way to go over each one of them. So in this session today, we will start talking about memory land. Now, this presentation was prepared by me and my friend Shadi Naif. So thanks to him. We did them a long time ago, but they are still very useful, and I would say they explain what we want when we talk about exploitation. So welcome to Memory Land again. Let's start. This is an outline, what's going to be covered, the topics here that we will be going over them. Some of them I will move much faster than the others for a reason that they were covered in previous sessions. So don't expect me to dive deeper into them, but you can go back and check the other videos or our other sessions for further understanding, or you can just check online references for doing that. So software exploitation introduction, let's start here. So at the end, a program is just a set of rules that they follow a certain execution flow which tells the computer what to do. And those, let's say those rules were defined by the developer of the program. So the developer set a, let's say, he defined or he set these certain execution flow that he wants it to do this, it goes there, it comes here, etc. And then when you run the program, that's what's going to happen. But for us, our goal is to exploit the program or exploit the software. So we want to get the computer to do what we want, even if the program was designed to prevent that action. So this is also part of the definition from The Art of Exploitation. Now, I know The Art of Exploitation is probably an old book. It's talking about when we compare where we are today, but still it has the basis, the basics, and it has, I'd say more than the basics actually. It has the core for software exploitation, and this definition is really what exploiting a program is about. So again, the developer created the program. The idea was to have that program do something, but we as, let's say, software, we want to do some exploitation to that software, or we want to exploit it, or maybe even a threat actor wants to exploit the software. So the idea or the goal is to get the program to do what we want, even if that program was not designed to do that, or they want to prevent us from doing that. This is not, by the way, something new. Again, if anyone is interested in history, this was documented back in 1972 by the US Air Force, or by a study in the US Air Force. So it's not something new. So it's 1972, that's a long time ago. And still, with the new mitigation techniques that are being developed by, let's say, which are, we will also talk about them, even with those new mitigation techniques which are being applied, whether by the operating system or whether they are applied by your hardware or even the compiler itself. Software, unfortunately, is still today exploitable, or we can still exploit these software or programs. So welcome again to the memory land. Now, what's needed to understand exploitation? Definitely you'll need some background with computer languages. It's good to have at least the basics. You don't probably need to be professional in them. It's good if you are, but if you don't, at least understand them. Operating systems is very important. I keep mentioning that, and I will continue doing that. And architectures, like understanding which computer are we targeting, and or let's say what program we are targeting, and what hardware is it running on. So those are the basics, I would say, that you need in order to understand exploitation. What will be covered in this session? A little bit about CPU registers, because again, we covered those in a different session. How functions work, we will focus on this, it's very important. Memory management, especially for the Intel 32-bit architecture or Intel x86. We won't be doing anything related to 64-bit. If we have enough time, I'll add that at the end of our classes, but for now we'll focus on Intel 32-bit architecture. Also, we'll need a little bit about, let's say, assembly. I assume by now you have a little bit of background with assembly and C. At least understanding the code. You don't need to be, at least for now, proficient with C or assembly, but at least you are able to read the code, understand it, and understand what's going on. Why do I need those? Because at the end, security holes come, most of them, I would say, most of them come from memory corruption. So that's why it's very important if you have a good background in what we just mentioned. Now, CPU instructions and registers. So the CPU at the end contains a couple, or let's say a number of registers, depending on its model and architecture. So whether the number of registers on a 32-bit system is on an x86, system is different than when we talk about a system, a 64-bit system. So keep that in mind. The number of registers will be different. In this session, we will be focusing on three main registers, which is the EBP, ESP, and EIP, which is the instruction pointer, and we'll talk about all of these. So these are the main focus in this session. Not that other registers are not important, but these are the main ones because we want to focus on exploitation and how things are working, especially when dealing with the stack, something which we will be seeing in a couple of minutes. Now at the end, the instruction is the lowest execution term for the CPU. So CPU will be executing instructions, while a statement is the high-level term that is compiled and loaded as one or many instructions. So you can think of instruction as the assembly code, and you can think which is being, let's say, executed by the CPU, and you can think of the statement, which is the program. Let's say it's written in C, but that code which is written in C, it could be more than one single instruction. Okay, so a statement could be multiple instructions. An instruction is just one single set of, let's say, one instruction. It will be one set of things to do. Let's say, let's call it that way, probably. So assembly language is a human-friendly representation of the instructions or the machine code. So assembly is, let's say, even though some people might say assembly is not easy, it is not easy, I would say, maybe. It depends also on, it depends on practice, really, I would say. But it's the human-friendly version of the instructions which the machine will be executing. At the end, the machine will be actually executing what is called machine code or byte code. We will also see those later in this course. CPU registers, just a quick overview. As you can see, we have the 16 bits, 32 bits, and 64 bits. And we can see that each one of them, like when we talk about the AX, which is the accumulator, that's what it's called, but it could be used for something else. BX, base index, CX, counter, DX, data, BP or EBP, which we are going to focus on 32 bits. So let's talk about that, which is the extended base pointer. Okay. ESP, which is this extended stack pointer. These are all 32-bit registers. EIP, which is the extended instruction pointer. And then we have ESI and EDI, which are two pointers for when we deal with strings or with data. Now, the register, the system can also access, let's say, lower and higher ends of these registers. So let's say we have the 16-bit, let's say the AX, the 16-bit, which is a 16-bit. We can access the lower word of the AX register by accessing the AL of that register, which is called AL. So that way we are accessing the lower word of that. If we want to access the higher word, then we will just go AH, and the same applies for BX, CX, and DX. Okay. Now these are again not the complete list of registers. Again, like 64-bit has more than this, but these are just an example. Now functions, a high-level view. We want to look at the functions, a high-level view, and see what makes a function, or what is a function, what does a function consist of. So here in this program, we have 3 different functions. If we go to the bottom, because that's where, let's say, the program will first start, I would say, at least for this session. So integer main, integer argc, char star argv, and then those brackets, etc. So this is the main function, which is the integer main. This is the main function, and inside it we have some if statement, which is going to be checking if the argument c is more than 1. So we have a decision to be made here based on the value which is passed on the value which is in argc. Argc is the argument counter, and if the argument counter is more than 1, then we will be calling a function called myfun1, and we will be passing the second argument to that function. Now if we go to myfunction1 or myfun1, then we see it's taking a pointer to a string. Inside there's a character buffer of 16 bytes. So we are creating a buffer of 16 bytes. It means our buffer is 16 bytes long. And then we are calling the strcpy, which is to copy the value which is going to be passed into str into our buffer. So whatever value the user will be entering, it's going to be copied to the buffer. And then that buffer is going to be passed to myfun2. If we go to myfun2, go up now again, we can see we get it's a pointer to a value. So we can see then print you entered %s/n and then x. So what's happening here is, let's say when you run the program, and then you let's say you send the argument like hello, what will happen is the program will take the value hello, or the string hello, it will copy it into the buffer, and then it will take that value which is now in the buffer, and it will send it to myfun2, and myfun2 will just print on the screen you entered hello. So that's basically how the execution will happen. We will be running this code and exploiting it, but that's going to be in a later video. For now, I just want you to understand the code, which is over here. So this is a high-level view of our functions. Now, these are the function names. So as you can see, these are the function names, and that's why we have this color so we can highlight them. Now, these are the parameters or arguments which are going to be passed to this function. Okay, these are the parameters, arguments passed to this function. And as you can see, the slides were prepared in a way that you can like navigate them with kind of animation, or kind of, let's say, help you understand which one we are focusing on in the slide. Now this is the body of the function. So each one of these, whether main, myfun1, myfun2, each one of them has a body. That's the body of those functions. And then at the end, this is the local variable definitions. So as you can see here, only myfun1 in this example has some local variable definitions. Okay. And then these are the return values. So when the function finishes its work, it's gonna have a return something back. So we can see main is going to be returning back an integer, myfun1 is going to be returning back nothing. So this is the return type value. Okay, that's going to be returned by this function. And now let's look at how the system will actually track the execution of this function. So let's say you compile this program and now you are about to execute it. We are not going to look now at the code from an assembly point of view, which is the lowest instruction, which we will be seeing, which the CPU will be, let's say, executing. But here we want to keep focusing on the functions, a high-level view, but see what will happen and how the execution flow is going to be done, how it's going to work. but we want to introduce the concept of the stack. So the stack is actually the best structure which the system could use to trace the program's execution. And you are going to see why. The stack is first in, last out. So when you put something into the stack and you add something on top of it, the first thing you put there is going to be the last one to like take out. You can think of it like the usually it's the, some people might refer to it similar to the example of some dishes. So you have or plates. You have a plate, and you put the first plate in the sink, and then when you put the second plate, it's going to be on top, the third on top, etc. Then if you want to take the first plate out, you'll need to take all of the first plates which are on the top in order to reach the bottom of them. So again, it's first in, last out. So that's what the stack is about, and you will understand when we go over this why the stack is used for program execution. It's a really good one. So if the current statement is going to be executed, you'll see it in this blue color. So let's start, let's say, executing our code. So what will happen is, first thing is the program main will start, and it's going to be checking whether the arguments counter is more than 1 or less, or 1 maybe. So if it's more than 1, then now the execution is going to go to myfun1, and we are going to pass the second argument to myfun1. Why is the second? Because the first one, argv0, is actually the name of the program. So argv1 is actually the first parameter to be passed. And don't forget that arrays start always with 0. So the first member in the array is actually argv0, which is again the name of the program. And then argv1 is the second, which is actually the first argument to be passed. So again, let's say we pass the value hello. Now hello will be sent to myfun1. So what will happen is myfun1 now gets pushed, let's say the position of myfun1 gets pushed where? Onto the stack. So now we are saving the position of myfun1. We go to myfun1. Now this is where the execution is going to happen. Now we are going to create a buffer for the character buffer with 16 bytes. Executions continuing. Now strcopy. Now this one is also a function, so we should be storing actually also the location, the position of strcopy here onto the stack. But for let's say making things simpler, we're just gonna like jump over it and like focus on the functions which we have in our code, not the functions which are provided to us by the libraries, which is strcopy is a function that you can use by the by a library that you import and you include and you start to use. So we are, if we were to trace this one step at a time, then we will be adding the position of strcopy to the stack and then continuing from there. But again, for making things simpler, we're just going to skip this and assume it was done. Now we are going to go to myfun2. We are going to pass the buffer. So the execution is here. myfun2, the position of that, we need to also push it where? Onto the stack. So we need to save the position of myfun2, okay, before we go and start executing it. Now, since we saved the position, now let's go and start executing. So we get there. Now we print the statement. So this statement will print the hello message, hello word that we entered. Okay. Now the execution has ended for myfun2. Where are we going to go back? Now the stack will be used to understand where was I and how can I continue from where I left from. So we are going to pop out the value or the position which is now on the stack. And as you can see, the top value on the stack was the previous function we were executing. So that's why the stack is very useful for program execution. Again, what we need to do now is, after we finished myfun2, we need to know how we can go back to where were we before we entered myfun2. We were in myfun1, so we need to understand how can we go back to there. Again, we are going to pop the position which is currently on the stack and then go there. So we pop there. As you can see, there is really nothing left in my fun1. If there was, it will be executed, but there's nothing here. So now what will happen? We need to now understand where were we before we came to my fun1. Like, what was the previous execution code that we were working on, or we were executing, or the system was executing before we started executing my fun1. Again, we'll go back to the stack. The stack will pop out the position of my fun1. It will tell the system that, hey, if you want to go back to the previous function, the position for that is over here. So it's going to pop that value out. Then we are going to come here, finish the execution, and then end of execution. So that's how the program will start and the execution will end. So we saw by looking at a high-level view how the function will work, how the stack representation, which is actually doesn't really exist in memory, it's something virtual, okay, but it's used for program execution. And now we can understand how the program was executed and how the stack was used actually to make sure once I go to another function, I know how I can go back to where I was before I went there. And the same thing when I go to that function, I know how I can go back to the previous function, and so on and so forth until the program ends its execution, like you can see here, end of execution. So stack and frames. There is no physical stack inside the CPU. Again, it's something virtual instead. Okay, the CPU uses the main memory to represent the logical structure of the stack. Again, there is nothing really in memory that is a stack. It's just it's not a physical part in the CPU or in memory that is being used to represent the stack. It's just a logical representation which is used to represent the stack. Now, the operating system reserves a contiguous raw memory space for the stack, and that happens at the immediate startup when you start the application, that the OS will reserve that value for you, okay? And the stack is logically divided into many stack frames. The stack is also logically divided into many stack frames. Each frame will be created when we call a new function. We will come to this in a little bit. Now, the stack and all the stack frames are represented in memory upside down. Okay, keep that in mind. The stack and all frames are represented in memory upside down. You will see in a minute what does that mean. But for now, just think of it like that. So stack frames, the stack frame is represented by 2 pointers. So we need, in order to be able to trace the stack frame and what's happening in the stack frame, we need to have 2 pointers. One will be pointing at the base, which is the base pointer, and that's EBP. That's the register EBP. So the register EBP will always be pointing at the base of of a frame. Okay. The memory address that is equal to EBP minus 1 is the first memory location of the stack frame. Keep that in mind. EBP minus 1, this is just an example, which will always be pointing to the memory location is the first memory location of the stack frame. Okay. Now, the stack pointer, which is used by, let's say, the ESP, which is the register ESP, which is the stack pointer, that will be pointing always to the top of the stack. So the memory address that is equal to ESP is the top memory location of the stack frame. Again, ESP will always be pointing to the top of the stack. And again, since our stack is divided into frame, you will see all of that in a minute. So even if you can't currently imagine how this is working, we will see it in some visual. ESP will always be pointing to the top of that frame in the stack. Okay. When you push or pop a value, ESP register is going to be changing. So when you push a value, ESP will change. When you pop a value, ESP will also be changed. So the register which will be changing depending on when you add a value or when you push a value to the stack or when you remove a value from the stack by pop is actually the ESP pointer. Okay. The base pointer, which is EBP, never changes unless the current stack frame is changed. Keep that in mind. Again, the base pointer will never change unless the current stack frame is changed. So if the current frame, which is active, gets changed, that's when EBP will happen. Again, all of this, maybe you'll say, what is this guy talking about? That's probably true. You'll understand all of this in a couple of minutes when we go to some visuals and have an idea about what's happening there. The stack frame is empty when EBP's value equals to ESP's value. So that's when we consider that the stack frame is empty. Now let's go and look at this and see what's going on. Again, like we said, we have the stack, it's upside down. So that's why you can see the top of the stack is always going to grow towards the lower end of the memory, and the start of the stack or the base of the stack is always going to be on the higher end of the memory. Okay, so when we push a value, when we add a value to the stack, it's growing towards the lower end of the memory. So what that means is the memory addresses will be decreased. Okay, keep that in mind. And when we remove a value from the stack, it's actually the memory addresses will be increased. Now here you can see the memories, because I just put this one from 00 to FFF, etc. Now this memory is always will be divided into two let's say spaces. One is kernel space and one is user space. Sometimes this is for Linux, will, let's say, use 1 gigabyte for kernel space, while the user space will have 3 gigabytes. Now all of that, so this means we have 4 gigabytes for a 32-bit application, but keep that in mind, this is all virtual. But for every single application, you'll have a virtual address space of 4 gigabytes. Okay, this could be changed, but again, this is the default, which for now we just want to explain the idea. So again, you have the stack. You can see here, there's a pointer pointing to the start of the stack. There's a pointing to the top of the stack. Again, remember, when we add a value to the stack, so when we push a value, the memory address is going to be decreasing. When we remove a value, the memory address is going to be increasing. Why? Because when we add, we are moving towards the lower end. When we are removing, we are moving towards the higher end of the memory. Let's continue. You'll understand more about this as we continue. So stack and stack frames inside the main memory. Again, this is the lower end at the top. You can see, not sure if you can see my mouse. This is where the lower end of the memory, this is the higher end of the memory, and we can see this is the top of the stack. We can see this is the bottom of the stack. So we can see here the stack has multiple frames. So all the stack frame, new stack frame. So one note to keep in mind is the stack frame, which is frame index number 0, will be the one that is actually active, and the oldest stack frame is indexed as stack frame count -1. So again, the one that's going to be active will be the stack frame 0. The one before it will be like number 1, and so on and so forth. So the newest stack frame is indexed as stack frame 0, the older one stack frame 1, and the oldest stack frame is indexed stack frame count -1, and so on and so forth. Okay, so keep that in mind. Yeah, so here we have 1, 2, 3 stack frames. So managing stack frames, let's see. Yeah, let's probably stop here and then continue. Yeah, we already have reached 31 slides. So let's stop here and continue in another video. So we'll start in managing stack frames in our next video. Thank you for watching this one.